Welcome to this problem walkthrough. Today, we'll explore problem number 636, exclusive time of functions. This is a fascinating challenge that tests your ability to manage logs and compute execution times efficiently. Let's dive in and break it down step by step. In this problem, we are tasked with analyzing the execution time of functions running on a single-threaded CPU. The input consists of the number of functions, denoted as n, and a list of logs. Each log is a string formatted as function_id, start_or_end timestamp, where function_id represents the function's unique identifier, start_or_end indicates whether the function is starting or ending, and timestamp specifies the exact time of the event. A key point to note is that the CPU can only execute one function at a time. Functions can also be nested, meaning one function might call another and wait for its completion before resuming. The goal is to calculate the exclusive time for each function, which refers to the time spent executing the function itself, excluding any time spent in nested function calls. The result should be an array where the value at index I represents the exclusive time of the function with id I. To better understand the problem, let's go over the input and output formats. The input includes an integer n, which represents the number of functions, and a list of logs. These logs are sorted in chronological order and describe the start or end of function executions, with timestamps that are strictly non-decreasing. The output is an array of integers result with a size equal to n. Each element in the array corresponds to the exclusive time of a function, where result, I, is the total exclusive time of the function with id I. For example, in the first example, we are given n equals 2 in logs such as 0 start 0 and 1 start 2. The output, 3, 4, indicates that function 0 has an exclusive time of 3 units, and function 1 has an exclusive time of 4 units. Now let's dive into the explanation of the examples. In the first example, function 0 starts at timestamp 0 but is paused when function 1 starts at timestamp 2. Function 1 then runs until timestamp 5, resulting in an exclusive time of 4 units, calculated as 5, 2 plus 1. After function 1 finishes, function 0 resumes at timestamp 6 and ends at the same timestamp. The exclusive time for function 0 is calculated as 6, 0 plus 1 is 4, which equals 3 units. Hence, the result is 3, 4. In the second example, there is only one function. Function 0 starts at timestamp 0 and ends at timestamp 1. It runs without any interruptions, so its exclusive time is simply 1, 0 plus 1, which equals 2 units. The result in this case is 2. Let's explore the third example. Function 0 begins at timestamp 0 but is paused at timestamp 2 when function 1 starts. Function 1 is also paused at timestamp 4 when function 2 starts. Function 2 runs exclusively from timestamp 4 to 6, giving it an exclusive time of 3 units, calculated as 6, 4 plus 1. After function 2 ends, function 1 resumes at timestamp 7 and runs until timestamp 8. Its exclusive time is calculated as 8, 2 plus 1, 3, which equals 4 units. Finally, function 0 resumes at timestamp 9 and runs until timestamp 10. Its exclusive time is 10, 0 plus 1 is 7, which equals 7 units. Thus, the output is 7, 4, 3. We can summarize the third example by breaking it down further. Function 0, which was paused during the execution of functions 1 and 2, resumes after they finish. Its total exclusive time is derived from the time it was active, minus any time spent in nested calls. Similarly, function 1 calculates its exclusive time by subtracting the time spent in its nested call to function 2. Function 2, on the other hand, has no further nested calls, so its exclusive time is simply the duration it was active. The constraints provided ensure that all function calls are well formed, meaning each function starts and ends exactly once, and timestamps are always in order. Additionally, the problem guarantees that there are no invalid scenarios, such as a function ending before it begins. Finally, let's consider some edge cases. If the log list is empty, such as when n equals 1 and logs equals, the output should be 0, because no logs imply no execution time. Another edge case involves a single function running without interruptions, where the exclusive time is simply the duration between its start and end timestamps. When multiple functions include nested calls, the problem ensures that we can systematically calculate the exclusive time by accounting for pauses and resuming execution. These cases highlight the importance of carefully managing the timestamps and stack operations to handle both simple and complex scenarios correctly. When tackling this problem, one of the first approaches we might consider is a brute force simulation of the function execution. The idea here is straightforward. For every log entry, we manually track the time a function starts and ends while also accounting for overlaps in nested function calls. To do this, we would parse all the logs, maintaining a timeline or counter to keep track of execution. Each time a function starts, we would mark its timestamp, and when it ends, we calculate its duration and subtract any time spent on child functions. However, this approach has significant drawbacks. The time complexity is quadratic, n squared, because for every start log, we would need to search for its corresponding end log, which becomes inefficient for larger inputs. Additionally, handling nested function calls manually can be cumbersome and error-prone. While simple to understand, this brute force method is not scalable or efficient for larger datasets with deeply nested calls. A more efficient approach leverages the fact that function calls are inherently nested, which aligns perfectly with the structure of a stack. Using a stack, we can track active functions and their execution times without needing to rescan the logs. Here's how it works: every time we encounter a start log, we calculate the elapsed time for the function currently at the top of the stack, then push the new function onto the stack. When we see an end log, we pop the function from the stack, calculate its exclusive time, and add it to our results. Throughout this process, we maintain a running timestamp to ensure accurate calculations. This approach efficiently handles nested calls because the stack naturally mirrors the nesting structure. By adjusting for time spent in child functions, we can calculate exclusive times incrementally, making this method both intuitive and performant. The optimized stack-based approach offers significant improvements in both time and space complexity. With a linear time complexity of O(n), we only process each log once, and the space complexity of O(n) is due to the stack used for managing active function calls. This method is highly efficient and scales well, even for large inputs with deeply nested calls. One of its key advantages is how naturally it handles nesting each start and end log pushes and pops functions from the stack, ensuring we always focus on the current active function. While we did consider alternatives, such as a two-pass solution or timeline simulation, these were less efficient. The two-pass solution involves additional processing to analyze the nesting structure, and the timeline simulation requires creating a timeline array, which can be highly inefficient for large timestamps. In contrast, the stack-based approach provides a clean, intuitive solution that eliminates unnecessary computations. Ultimately, we chose the optimized stack-based approach because it strikes the best balance between simplicity and efficiency. The stack mirrors the nested structure of function calls, allowing us to calculate exclusive times in a single pass while maintaining a running timestamp. This alignment with the problem's constraints, such as sequential logs and unique function IDs, makes the stack-based method particularly effective. Key observations that influence this choice include the ease with which nested calls can be tracked using a stack and the incremental nature of exclusive time calculations. While the brute force method is simpler to implement, its inefficiency makes it impractical for larger inputs. Similarly, alternatives like the two-pass solution or timeline simulation are more complex and less efficient. By leveraging the stack, we minimize computation and handle nested calls elegantly, making this the most robust and scalable solution for the problem. In this problem, we need to calculate the exclusive execution time of each function based on its execution logs. Each log specifies whether a function starts or ends, along with the corresponding timestamp. The exclusive execution time of a function refers to the time it directly spends executing, excluding any time consumed by nested function calls. To tackle this, we start by parsing the input logs, which follow the format function_id action timestamp. Here, the function ID identifies the function, the action indicates a start or end event, and the timestamp tells us the time at which the event occurs. Next, we initialize two key data structures. The first is a stack, which will help us manage the sequence of function calls and track their start times. The second is a result array, sized to match the number of functions, where each index represents the exclusive time of a specific function. Initially, all entries in the result array are set to 0. These preparations set the foundation for processing the logs efficiently. To compute the exclusive execution times, we iterate through the logs one by one. For each log entry, we parse it to extract the function ID, the action, and the timestamp. Depending on the action, we handle the log differently. When we encounter a start action, if the stack is not empty, it means another function is currently executing. In this case, we calculate the elapsed time for the function at the top of the stack by subtracting its start time from the current timestamp. This elapsed time is added to the result array for that function. We then push the new function and its timestamp onto the stack. On the other hand, when we encounter an end action, we pop the top function and its start time from the stack. The exclusive time for this function is calculated by subtracting the start time from the current timestamp and adding 1, as the function ends at the end of the timestamp. This time is added to the result array for the popped function. If the stack is not empty after the pop, we also adjust the start time of the next function on the stack to ensure it excludes the time spent in the just ended function. This step-by-step processing ensures that we correctly compute the exclusive execution time for all functions. Once all logs have been processed, the result array will contain the exclusive execution time for each function. This array is then returned as the final output. There are a few key insights to highlight here. First, the stack plays a critical role in managing nested function calls. Whenever a new function starts, it is pushed onto the stack, and when it ends, it is popped, allowing us to always track the most recently active function. Second, the precise management of timestamps is essential for accurate calculations. For a start log, the execution time of the current function is updated up to the point when the new function begins. For an end log, the duration is calculated and includes the entire interval by adding 1 to the timestamp difference. Lastly, the result array is updated efficiently in constant time for each log entry, ensuring that the algorithm operates with a time complexity of O(n). These insights underline the importance of the stack and efficient timestamp handling in solving this problem. To summarize the key data structures used, we rely on a stack and a result array. The stack is used to track active function calls, storing their IDs and start timestamps. This enables us to efficiently manage nested calls by maintaining a last-in, first-out order. The result array, on the other hand, stores the exclusive execution time for each function. It is updated directly during the traversal of logs, making the process both efficient and straightforward. Regarding the algorithm's complexity, the time complexity is O(n), where n is the number of logs. Each log is processed exactly once, and operations such as pushing to or popping from the stack, as well as updating the result array, all take constant time. The space complexity is also O(n), where n corresponds to the maximum depth of the call stack. This occurs in scenarios where functions are deeply nested. Together, these structures and their efficiency make the algorithm scalable and well-suited for large inputs. To better understand the algorithm, let's walk through an example with the input logs 0 start to 0, 1 start to, 1 end 5, 0 end to 6. First, we process the log 0 a start 0, pushing function 0 onto the stack with a start time of 0. The result array remains 0, 0. Next, for the log 1 start 2, we update the exclusive time of function 0 to 2, since the new function starts at timestamp 2. We then push function 1 onto the stack. The result array becomes 2, 0. Now, processing 1 end to 5, we pop function 1 from the stack. Its exclusive time is calculated as 5 minus 2 plus 1 is equal to 4, and the result array updates to 2, 4. Finally, for the log 0 end to 6, we pop function 0. Its exclusive time is calculated as 6 minus 0 plus 1 is equal to 7, but we subtract the 4 units spent in the nested function, leaving 3. The final stack is empty, and the result array becomes 3, 4. This step-by-step breakdown illustrates how the algorithm handles nested and sequential function calls. The final output for the example logs is 3, 4, which represents the exclusive execution times for functions 0 and 1, respectively. It's also important to consider edge cases that the algorithm handles effectively. For instance, in the case of a single function, such as logs, 0 start to 0, 0 end to 1, the result would be 2, accounting for the inclusive duration of the function. Another scenario is deep nesting, where multiple functions are nested within each other, as seen in the logs: 0 start 0, 1 start 1, 2 start 2, 2 and 3, 1 and 4, 0 and 5. Here, the algorithm correctly calculates the result as 1, 2, 2. Lastly, in cases of overlapping functions, the algorithm ensures accurate updates to the result array by appropriately handling nested calls. These examples highlight the robustness of the approach in handling a variety of inputs, ensuring correctness and efficiency in all scenarios. Here, we are defining a solution to the problem using a class and a method called exclusive time. The function takes two parameters, n, which represents the number of functions, and logs, a list of log entries. We first initialize an array called result, with a size equal to the number of functions, to store the exclusive execution time of each function. The array is filled with zeros initially. Next, we create an empty stack that will help us keep track of the function currently being executed, along with its start time. The logs list is iterated over, and for each log entry, we split it into three components: the function ID, the action, start or end, and the timestamp. These values are converted to integers where necessary. If the action is start, we check if the stack contains any function. If it does, we update the exclusive time of the function at the top of the stack by adding the difference between the current timestamp and the start time stored for that function. Then, we push the current function ID and its start time onto the stack. However, if the action is end, we pop the top element from the stack, which gives us the function ID and its start time. The duration of this function's execution is calculated and added to its corresponding entry in the result array. Additionally, if the stack is not empty after popping, we prepare to update the start time for the function now at the top of the stack. At this point, if the stack is not empty, we update the start time of the function at the top of the stack. We do this by setting the top of the stack to a tuple containing the function ID and an adjusted start time, which is the current timestamp increment by 1. This ensures that any subsequent function will have a properly updated reference point for its timing. Finally, after processing all the logs, the result array, which contains the exclusive execution times for all the functions, is returned. This array represents the solution to the problem, as it accurately computes the time spent exclusively by each function while accounting for nested calls and overlaps. Here, we begin by importing the necessary packages and defining our solution class. The exclusive time method takes two inputs: the number of functions n and a list of logs that describe the start and end events of these functions. We initialize an array called result to store the exclusive execution time for each function. Additionally, we use a stack to keep track of the currently running function and its start time. As we iterate through the logs, each log entry is split into three components: the function ID, the action, and the timestamp. If the action is start, we first check if the stack is not empty. In that case, we update the exclusive time of the function currently at the top of the stack by adding the difference between the current timestamp and its start time. Then, we push the current function and its start time onto the stack, effectively marking it as the active function. If the action is end, we handle the completion of the function. The last function is popped from the stack, and its execution duration is calculated as the difference between the current timestamp and its start time, plus 1 to include the ending moment. This duration is then added to the respective function's exclusive time in the result array. If there are still functions in the stack after this, we update the start time of the new top function to the next timestamp, accounting for the fact that the just-ended function has now relinquished control. Finally, once all logs are processed, the result array containing the exclusive times for all functions is returned. Here, we start with a simple example where there's only one function call. The input specifies n equals 1, meaning there's just one function, and the logs describe its start and end times. First, we initialize two variables, result, and array to store the exclusive time for each function, starting with 0 and stack, which will help us keep track of active function calls. Now, we process the first log, which indicates that function 0 starts at timestamp 0. After parsing the log, we see the action is start, so we push the function ID and timestamp as a tuple, 0, 0, onto the stack. At this point, the stack contains one entry, 0, 0, and result remains 0. Next, we process the second log, which marks the end of function 0 at timestamp 2. After parsing, we pop the top of the stack, which gives us 0, 0. Using this, we calculate the function's execution time as 2 0 plus 1 equals 3 and add it to result 0. The stack is now empty, and result becomes 3, which is also our final output for this example. In the second example, we're dealing with two functions, one nested within the other. The input specifies n equals 2, indicating two functions, and the logs describe their start and end times. First, we initialize result as 0, 0, to store the exclusive times for both functions, and stack as an empty list. Processing the first log shows that function 0 starts at timestamp 0. We parse the log and push 0, 0 onto the stack. Now the stack contains 0, 0, and result remains 0, 0. Next, the second log indicates that function 1 starts at timestamp 2. At this point, function 0 is still running, so we calculate the time spent by function 0 so far as 2 0 equals 2 and update result 0 to reflect this. Then, we push 1, 2 onto the stack. The stack now contains 0, 0, and 1, 2, while result updates to 2, 0. Moving on, the third log marks the end of function 1 at timestamp 5. We pop 1, 2 from the stack and calculate its execution time as 5, 2 plus 1 equals 4, adding this to result 1. Afterward, we update the start time of the function at the top of the stack to 0, 6, reflecting the adjusted start time of function 0. At this point, the stack contains 0, 6, and result becomes 2, 4. Now, we process the fourth log, which marks the end of function 0 at timestamp 6. Parsing the log, we pop 0, 6 from the stack. The execution time for function 0 is calculated as 6, 6 plus 1 equals 1, and we add this to result 0. With this update, result becomes 3, 4. Since the stack is now empty, we've processed all logs, and the final output for this example is 3, 4. This demonstrates how nested function calls are handled, with the outer function's exclusive time adjusted based on the inner function's execution period. In the third example, we explore overlapping function calls. The input specifies n equals 2 for two functions, and the logs describe their start and end times. We initialize result as 0, 0, and stack as an empty list. The first log indicates that function 0 starts at timestamp 0. We parse it and push 0, 0 onto the stack. At this point, the stack contains 0, 0, and result remains 0, 0. The second log shows that function 1 starts at timestamp 1. Since function 0 is already running, we calculate the time spent by function 0 so far as 1 is 0 equals 1 and update result 0 accordingly. Then we push 1, 1 onto the stack. The stack now contains 0, 0, and 1, 1, while result updates to 1, 0. Next, the third log marks the end of function 1 at timestamp 4. We pop 1, 1 from the stack and calculate function 1's execution time as 4, 1 plus 1 equals 4, adding this to result 1. We also update the start time for the function at the top of the stack to 0, 5, to reflect the adjusted start time of function 0. Now, the stack contains 0, 5, and result becomes 1, 4. Finally, we process the fourth log, which marks the end of function 0 at timestamp 5. Parsing the log, we pop 0, 5 from the stack. The execution time for function 0 is calculated as 5, 5 plus 1 equals 1, and we add this to result 0. With this update, result becomes 2, 4. The stack is now empty, and we've processed all logs for this example. The final output is 2, 4, which illustrates how overlapping function calls are handled, with each function's exclusive time calculated correctly based on its start and end timestamps. Let's continue with the next part. The time complexity of our solution is determined by how we process the input logs and manage the stack operations. Parsing the logs involves splitting each entry into three components: function ID, action, and timestamp. This splitting and the subsequent conversion of function IDs and timestamps into integers are constant time operations for each log. Since there are m log entries in total, parsing contributes an overall time complexity of O(m). Next, we have the stack operations. For each start log, we push a tuple containing the function ID and timestamp onto the stack, which is an O(1) operation. For n logs, we pop a tuple off the stack, which is also O(1). In addition, updating the result array for a function's execution time involves simple arithmetic operations, also performed in constant time. Since every log entry results in at least one stack operation, the total contribution from stack operations is O(m). By combining the parsing and stack operations, the overall time complexity of the solution becomes O(m). The space complexity of this solution accounts for the memory used by the result array, the stack, and temporary variables. First, the result array stores the exclusive execution time for each of the n functions. This requires O(n) space. Then, we have the stack, which is used to keep track of active function calls. In the worst case, the stack might need to store all the active start logs. Since there are at most m log entries, the stack could grow to O(m) in size in the absolute worst case. However, in more practical scenarios, the stack size is limited to O(n) when nested calls involve at most n distinct functions. Finally, temporary variables like func_id, action, and timestamp are used for intermediate computations, but they only require O(1) space. When we combine the memory requirements of all these components, the overall space complexity of the solution is O(n plus m). When comparing this solution to a brute force or naive approach, we see a clear improvement in efficiency. A naive solution would involve iterating through the logs repeatedly to calculate the exclusive time for each function. This repeated traversal results in a time complexity of O(m squared for m log entries. In contrast, the optimized solution uses a stack to efficiently manage nested calls and keep track of running states, reducing the time complexity to O(m). The best-case scenario occurs when all function calls are non-nested and sequential, where each log entry leads to a single stack operation, resulting in O(m) complexity. In an average case, where there is a mix of nested and non-nested functions, the stack dynamically grows and shrinks, but the overall time complexity remains O(m). Even in the worst case, with all functions deeply nested and the stack growing to its maximum size, the complexity still remains O(m) due to efficient parsing and stack operations. Mathematically, the solution's efficiency can be justified as follows. Each log entry is processed exactly once during parsing, leading to a linear time complexity of O(m). This is complemented by the stack operations, which are constant time for each push or pop and together contribute O(m) as well. For space complexity, the stack size is bounded by the number of active functions or log entries, whichever is smaller, making it O(n plus m). The result array contributes O(n), and temporary variables use O(1) space, leading to an overall space complexity of O(n plus m). By avoiding redundant computations, such as repeatedly traversing logs as in the naive approach, the solution achieves optimal performance with a time complexity of O(m). This balance of linear time and efficient space usage highlights the effectiveness of the optimized approach. Let's discuss some common mistakes candidates make when solving this problem. First, misinterpreting the problem statement is a frequent issue. For example, some overlook that the logs are already sorted or misunderstand the relationship between a function's start and end times. It's crucial to clarify these input details before diving into the code. Another challenge is handling nested functions. When a child function starts, the parent function's execution is paused. Failing to account for this nested behavior can lead to incorrect results. Next is the improper choice of data structures. While a stack is ideal for tracking active function calls, some candidates use arrays or other structures, which often complicates the logic unnecessarily and introduces bugs. Then, there are off-by-one errors, such as calculating time intervals without accounting for the inclusive nature of the end timestamp, which is a common trap. Finally, inefficient parsing of logs, such as multiple traversals of the input or suboptimal string operations, can increase runtime and hurt performance. A single traversal with efficient parsing techniques should always be the goal. Now let's look at some key insights for interviews. Recognizing the stack-based processing pattern behind this problem is critical. This pattern appears in many sequential event-based problems and can save you significant time if you identify it early. Edge cases are another area to focus on. Logs with just one function, deeply nested calls, or cases where no function ends can all introduce complexity. Optimization is also essential. While brute force methods might work for small inputs, interviewers typically expect an O(n) solution, where n is the number of logs. It's important to explain your thought process thoroughly. For example, How are you managing nested calls? How are you pausing and resuming parent functions? How are you tracking and calculating exclusive times? A clear explanation demonstrates not only your coding skills but also your understanding of the underlying mechanics. Additionally, there are related problems that follow similar patterns, like LeetCode 735 for asteroid collisions, which involves decision-making with stacks, and LeetCode 394 for decoding strings, which is another nested structure problem. Preparing for these can help you recognize similar approaches in interviews. Finally, let's consider some alternative approaches and their trade-offs. One option is brute force with timeline simulation. This method involves iterating through the entire log and simulating execution times for each timestamp. While it's conceptually straightforward, it's highly inefficient with a time complexity of n*t, where t is the total time range. This makes it impractical for large inputs. The optimized stack-based approach, on the other hand, is much more efficient. Here, a stack is used to track active function calls. For each start log, the function is pushed onto the stack, and for each end log, the function is popped, allowing you to calculate exclusive time while adjusting for nested calls. This approach runs in O(n) and is the preferred solution, but it requires careful handling of edge cases to get right. Another less common approach involves pre-processing logs for parallel execution, splitting them into smaller chunks for distributed systems. While this shows creative thinking, it's overly complex for interviews and rarely needed. Each method has its trade-offs, but understanding these options helps you appreciate the efficiency and practicality of the stack-based solution. Great job making it to the end. In this video, we explored a stack-based solution for problem number 636 and discussed its time and space complexities. Remember the importance of stacks for managing nested contexts and how parsing logs can help solve similar challenges. Thank you for watching, and don't forget to like, subscribe, and stay motivated in your coding journey. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!